Wave scattering is a phenomena we experience on a daily basis. In this video, we identify different regimes of scattering using the numerical technique finite difference time domain. This video is submitted by Anmol Gupta, Anshul Jain and Vatsal Gupta. Let us look at some of the concepts we'll be running through in this video. Firstly, there are three kinds of scattering: relay scattering, Mie scattering and geometrical optics. Secondly, we have used perfectly matched layers for our simulation purposes, since we can't simulate an infinite computational domain, and truncating a finite computation domain generates unphysical and numerical reflections from the borders. Next, for resolution, the Courant stability parameter comes into picture. In FDTD, the space and time steps are linked by the given equation. For source, we have used a point and continuous wave source, and the obstacle is a vertical line of metal. This is the list of parameters we have used for a simulation exercise. All the dimensions are in programs unit. Also, it should be noted that for the various simulation purposes only the size of the metal block was changed. In the first case, the wavelength is much larger than the obstacle size. This corresponds to the relay scattering. As we can see, the field is majorly undisturbed by the presence of the obstacle. This is the MEEP code for the simulation for the above field. The blue color for the sky can also be attributed to relay scattering, since it is inversely proportional to the fourth part of wavelength, scattering the shorter wavelengths less and the longer wavelength much. In the second case, the wavelength is approximately equal to the obstacle size, and this is Mie scattering. And we can see that the diffraction starts occurring at the edges of the obstacle. In this MEEP code, we have only changed the size of an obstacle. For Mie scattering, all wavelengths of visible light are scattered approximately identically, and therefore the clouds appear to be white. For the last case, we have wavelength much smaller than the obstacle size, and we could practically see what happens for geometrical optics. In the feed plot, we can see that an interference pattern is observed in front of the metal and no field passes beyond the metal. Again, in the MEEP code, only obstacle length is changed. Geometrical optics finds its major application as optical fiber for communication. In the last segment, we try to reason the coloring of opalescent glasses. Opalescence is a type of dichroism seen in highly dispersed system with little opacity. The material appears yellowish red in transmitted light and blue in the scattered light. As shown in the image, the stone appears blue from the side, but orange light shines through. The strong contrast in refractive index between pores and solid part of sintered alumina results in very strong relay scattering, with light completely changing direction each 5 micrometers on average. Thanks for watching the video.